This is section 9.3, Graphs of the Sine and Cosine Functions. Before we get into the graphs of those particular two functions, I'd like for you to look with me at an idea that I think is understandable. The idea of periodic functions. There are a lot of things that occur in a predictable pattern. Weather over the years, although there are changes, of course, but generally speaking, summers are hot, autumn cooler, winter fairly cold in Texas, spring cool and nice, and then summer we repeat. The sine and cosine functions repeat their values over and over in a regular pattern because, as we saw earlier, the coterminal angles have the same trig function values. So whether it's pi or 3 pi or 5 pi or 7 pi, the trig function values for all of those would be exactly the same. So the trig functions are all periodic, and what is a hallmark for periodic functions is the following. If you have, and this is not going to be one of your trig ones, I'm just going to make up something that's periodic, and you'll have to kind of give me a little of a bit of understanding if this isn't perfect. Okay, so that's supposed to be one version, and then it repeats itself. I didn't give myself enough room over there. Oh, well, that's okay. Okay, so even though it's not perfectly drawn, hopefully you get the idea is that this is repeating itself over and over. Now, there are some vocabulary items that I'd like to introduce. The period of the function is the shortest length it takes for repetition to start occurring. Okay, it's the smallest possible value p. In the following equation. And that equation is basically something that's going to help us understand what it means for something to be periodic. That if you were to take a value of x, let's say at 0, which has this y value right there, when that occurs again, here and then here, that is an example x, which we can tell very easily is the same place in the pattern. So let me extend this a little bit to the left so you can kind of see how that would be true. That is supposed to be, if I were able to draw that so it looked the same, that particular point or any other point I could pick. Let me pick another one just so you can see. Let's see. Let's pick this point right here. That's repeated here and here. And notice that the spacing between those horizontally is a consistent distance. And it doesn't matter what initial point you started with, that distance is the same length here in pink as it is in green. Those horizontal distances between subsequent occurrences of this same value in the same pattern, that's what we call the period. So the length of that, let's look at the green one, I guess, is just as well as anything else. The length of that, and the length of any of these arrows I drew is the same, is 1 period. So that's the length of that is the period. And so what that shows up as is down here is that you could start at f of x like 0, and then you'll have a repetition when the x value is, let's say, 1p later. And then you'll have another repetition 2p later. And so the distance we're moving horizontally between these relatively same positioned points, that length is the period, and we can start at any x and add a multiple of that period. So n is the integer multiple of the period, and if you do that, the y values will be the same no matter what x you pick. I happen to pick two pretty easy to identify. The one that kind of starts that linear piece, and the other one in green is where it's kind of in the middle of that linear piece. But any point on this graph, just pick any random point, and p later, you'll have the same thing happening. So p later, you're going to be at the same point. And p later, you're going to be at that same point. Okay? So any random point you pick, any multiple of p after that, you'll get the exact same y value. And that's what makes this periodic. So n is an integer. That's important to know. So any integer multiple of the period will get you back to the same relative position in the function. Okay, so that's what period is. So let's graph our first trigonometric periodic function. All 6 of them, by the way, are periodic, just so you know. But we're going to start with sine and then later cosine. As you know, or I hope you know or remember from the first times you did graphs, way back in maybe middle school, early high school, when you first did graphs, one of the ways you start with something that's new to you is to make a table of values and plot all of the points you get for that and look for a pattern. So way back in early times, I'm hoping this is true for a lot of you, that maybe late middle school or early high school, you first graphed a line for the first time. And at first you might not have known that that equation would produce a line, but after a while you got to be able to recognize the equation of a line, and you didn't have to plot 17 or 20 points to prove to yourself that again it was a line. You could graph for a line a minimum of 2 points. Like if you had the slope-intercept form, you could graph the y-intercept and use the slope to get a second point, and knowing that it was a line, you could finish that graph very quickly. Parabolas, kind of a similar thing. At first you might not have known what you were getting, but after a while you started recognizing what kind of equation produces the shape that you're learning about at that time. So that's what we're going to do here. It is a little bit tedious to calculate and plot all of these points. And of course, that's why we want to, as quickly as we can, look for patterns and look for easy things that will help us graph this a little bit more efficiently than making a table of values. You might notice here that in my table, I have quite a few in the first quadrant, almost all of our special angles. And then after the first quadrant, we know that using reference triangles, we'll get the same answers, although they might be negative instead of positive, but they're the same numbers. And we can use that fact to help graph this pretty well. So The sine of 0 is 0. The sine of pi over 6 is 1/2. The sine of pi over 4 is square root of 2 over 2. All of these are from earlier work that we went through. The quadrantal 0 and pi over 2, sine is 1. Sine of pi is 0. Sine of 3 pi over 2 is -1. Sine of 2 pi is 0. Those are the quadrantals we did already. And then we did the special 30, 60, 90, and 45, 45, 90 right triangles to get these answers. So all of this is to be found in work that we've already done. So I'm just basically recording all of these values for you. Okay, so one of the things you might notice is that we're in radians, and almost all the time that's going to be a true thing in this course. We're moving toward radians and away from degrees. However, there will be a few units where we go back and focus on using degrees almost exclusively, like when we're doing triangles, solving triangles. We'll use degrees for that. But here in radians, I want you to notice how I'm going to mark the x-axis off. I don't want to put 1, 2, 3, 4. Instead, the generally accepted size of one mark in the x-axis is going to be pi over 2. For the majority of the basic graphs we do, that's very adequate. And so every pi over 2 is what I'm representing with a mark. So that's, and I only need to mark the first one in the positive direction on the x-axis, because you can then assume that the second one is 2 pi over 2, which is pi. The next one's 3 pi over 2. The one after that's 2 pi. And over to the left, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. On the y-axis, if we don't want a distorted graph, I want you to think about the decimal value we had for pi over 2 is about 1.57. So if the length, this length right here is about 1.57, then imagine how long 1 would be. And it's not perfect, of course, but would you agree that 1 would be about maybe that long? So if we don't want to have a distorted graph on the y-axis, we're going to mark off our 1s, and they're shorter than the marks on the x-axis. And that's going to make it a non-distorted graph. I don't know if you recall ever graphing like a circle, and if you didn't have the scale right, it would look like an ellipse, kind of an ovoid shape, and it wouldn't look very good. That can be caused by distortion of the graph. Even on a graphing calculator, if you have this squared up, distorted view of the scale, when you graph a circle, it might not look like a circle. So that's kind of an important thing to think about. Now, we're intentionally going to distort graphs later, and we're not going to worry too much about this, but it's with our foreknowledge that we do that. So for right now, I'm trying to make everything look as perfect as I can, so that whatever shape you see here is actually the correct shape, not distorted. All right, so I'm going to start plotting some points. 0, 0. Pi over 6. Of course, if this is pi out that far, that's the second mark over. If that's pi, what I want for pi over 6 is 1/6 of that. So I'm going to eyeball where that is, and it's not perfect. Just go with it, if you will. And that will give me a y value of 1/2. And we are kind of guessing where that is exactly. Then the next one at pi over 4, oops, actually I want to back up and redo that. It's actually more like right here. There we go. At pi over 4, which is actually exactly halfway between 0 and pi over 2, the answer is square root of 2 over 2. That's about 0.707. Don't ask me why I know that number. I think it has something to do with my dad, the engineer, drilling some of these into my head. At pi over 3, so about 1/3 of the length of pi, I'm going to graph square root of 3 over 2. It seems like this is this is one I didn't memorize, and I probably should have. So I'm going to type it in my calculator so that I know sort of what it is. Of course, on this scale, I'm guessing 0.866. Okay, so pi over 3 should be 0.866. And pi over 2 is 1. Okay. Then pi is 0. 3 pi over 2 is -1. 2 pi is 0. And what's happening in between 0 and pi over 2 is a nice curve, nice smooth curve that looks like this. There we go. And with the same values in the second quadrant, as we move around, we're going to get a repetition of those sum values. So you should see that the left side of this, to the left of pi over 2 and to the right of pi over 2, should look the same. Of course, without my being able to draw perfectly, it's not perfect. And then the same values happen between pi and 3 pi over 2, but they're negative. And so the same shape is used. And then from 3 pi over 2 to 2 pi, same thing happens. And that's one period of the sinusoid, because you know that to get the same answer for coterminal angles, like 0 and 2 pi are both 0, they're coterminal. And so after that, we'll just continue in that pattern. And I do want to say that I'm going to draw the x-axis a little bit longer than I started with. Let me draw a few more marks on this axis. So we're going to start seeing repetition. And if you know what this shape looks like now, that's what its shape is. And the name of the shape, by the way, that's a sinusoid. That's the name of this shape, is a sinusoid. It's actually sufficient if you graph just a very few of these points. I'm going to refer to these points by a certain kind of naming that I've made up. It lets me graph really quickly. So I call the values that are right now on the x-axis, I call those middle values. And the ones that are at the 1, that's the highest value, so I call that a high value. And the value at -1 is a low value. And so the pattern is middle, high, middle, low, middle, then high at 1, middle at the x-axis, low at -1. The next one would be middle again, and we'd see repetition. I don't think I got the scale right, so it's kind of squeezed up there, unfortunately, because I didn't plan for it well. But that's now 2 cycles of that graph. So if we want to extend it to the left, we go backwards. Let's start right here. High, move to the left, low, high, middle, low, middle, high, middle, now low, middle, high, middle, and then connect those dots with the sinusoid shape. So very quickly, we're not having to graph a whole bunch of calculated points. We're graphing middle, high, middle, low, middle, and that's a cycle. And then we repeat for as many cycles as we're requested to do. This, of course, is 3 cycles long. Typically, I'm going to ask you to graph a minimum of 2, which I could also refer to that as 3 periods. Usually, I want you to do a minimum of 2, because I want to double check that you didn't just accidentally do the first one correctly. If you can do the second one correctly as well, then I know that you're on the right track. And a good way to do that is the original x and y axes that I had drawn. If I had done the right side to 2 pi and the left side to -2 pi, that's 2 cycles. Because -2 pi to 0, -2 pi is coterminal with 0, and then 2 pi is coterminal with 0. So that would complete 2 full cycles, going from -2 pi to 2 pi. And so that's generally what we'll do. Okay, so let's make a few observations about this graph and use some of the terminology that you learned in prior courses to kind of bring this full circle. The domain, That's the set of values that we're using for our independent variable. In this case, that's x. Well, we could keep going forever and ever, to the left and to the right. So the domain of this is all reals. And in fact, that's generally speaking what you want the domain to be. And the only reason it sometimes isn't all real numbers is if you're trying to divide by 0 or trying to take the square root of a negative number, for example. Anything that doesn't give you a real number answer has to be thrown out of the domain. But we do start with the idea that we want it to be all reals. Okay, the range is the set of outputs you get if you use every member of the domain. So in other words, what y values do we get? Well, we get a low value of 1, and it's included. If it were an open circle at -1, we would have a parenthesis instead of the bracket. So low value is -1. And we always go from low to high in this interval notation. Comma, the highest value you have for y is +1. Okay. It is a continuous function. No gaps, no skips, no vertical asymptotes, nothing odd like that. So it's just very nice, continuous, smooth function. Okay, where are the x-intercepts? Well, there are infinitely many of them, right? Because it goes on forever in that same vein. So we're going to learn how to write the answer to what are the x-intercepts in kind of a general way. So let's list them down here for a second. The x-intercepts are 0, and then pi, and then 2 pi, and 3 pi, and 4 pi, and 5 pi, and 6 pi, and 7 pi, etc. Then -pi, -2 pi, -3 pi, etc. forever. And so is there a generic way we can write an expression that gives us every one of those? And keep in mind, we want to use n very frequently here, where n is an integer. So if you look at these answers, aren't they all some integer multiplied by pi? See, we're getting answers in this list that are multiples of pi. So the way to write that is to write an integer multiple of pi looks like this. So if you substitute in integer -3, you'll get the first one in my list over there at the bottom left. Substitute in -2 for n, you'll get the second one that I have visible. -1, 0, 1, 2, 3. It will give you all of those answers. If you use every integer, you'll get all of them. Okay? The period length is the horizontal distance between subsequent points that are in the same relative position. A good point to use, because the middle is not a great one to use for that, and I'll tell you why. Because you have this middle when the function's on its way up, and then you have this middle when it's on its way down. Those are not actually the same idea. They have the same y value, but they are not the same idea. One's when the function's increasing, the other one's when it's decreasing. So I'd have to actually go all the way to here to get the next time that the function passes through the middle point on the way up to find the period. And so that's 1 pi over 2, 2 pi over 2, 3 pi over 2. That's at 4 pi over 2, 2 pi. So the period is 2 pi. And you can do it with the middles as long as you're careful that they have to be doing the same thing at that point. Another way to do that, to find the period, which I find easier, is to go like from high point to next high point. And that is easier to recognize. So if you count with me, starting at this one, I'm going to go 1, 2, 3, 4 marks to get to the next time. And if each mark is pi over 2, 4 times pi over 2 is 2 pi. So the period is 2 pi. 4 marks is the same as saying 2 pi if each mark is pi over 2. So that's the period, and it's 2 pi. Now, let's talk about symmetry. Do you see the symmetry of this one? It's symmetric with respect to the origin. And I think I might need to review that concept very quickly. So let me just write this down. Symmetric with respect to the origin is the type of symmetry this one has. And by the way, that means that it is an odd function. All graphs that are symmetric with respect to the origin are odd as a type of function, and that implies that if you put negative x into the function, you get back the opposite of f of x. And so for that reason, we're going to add to your list of identities to know a set of them called the even odd identities, and we're going to add to this list slowly as we graph each of the functions. So this is not going to be a complete list yet, but give this a place in your notes where you're keeping all of your things to memorize. And there will be 6 of them total, because we're going to address all 6 of the trig functions eventually. We're doing sine first, so the fact that it's odd means that if I were to take the function sine and substitute into it with the opposite of x, I would get back the opposite of the original function. So that's the odd identity for sine. So some of the trig functions will be odd, some will be even, and we'll discover those as we go. Okay, now just what does it mean for a function to be symmetric with respect to the origin? Let's talk a little bit about that before we get too far away from this graph. I want you to be able to see it. So if a function is odd, that means that if you were to look at its graph and pick any points you want on the graph, if you were to draw a line segment from there to the origin and measure it, and then continue in the same line, the exact same distance, you will land on a point that is on the graph. Okay, so let me do another one. Let's say this point is on the graph of our odd function, and if I were to measure that distance and then continue in the same line the exact same distance I went, then that point will definitely be a point on the graph of this function. And so I'm going to draw one and try to create something that's definitely an odd function. Not my best drawing ever, but for any point you pick on the curve, if you were to measure the distance to the origin and then continue in the same line, the same distance, you will find another point that's on your function. Okay? So that's what symmetry with respect to the origin means. And I'm kind of messing up this graph that I have up here because I'm doing so much drawing on it. So I kind of apologize for that. But pick, for example, this point right here. And if I were to go to the origin and then the same distance beyond the origin, there's another point that's on the curve. Okay? And that would be true wherever I decided to pick a point. There'll be a point on the other side of the origin that is the same distance from the origin that's on the graph for sure. So that's what an odd function is, and sine is an odd function. All right, so I think that's all I wanted to talk about with sine. So let's move to cosine. And we're going to try to address all the same topics. Hopefully I don't forget any of them. So again, we don't know exactly what cosine is going to look like. So we start with the idea of, well, we're going to plot lots of points and use what we've already talked about in prior lessons to kind of expand our vision of what it's supposed to look like, using all the information that we've gathered as we've gone along. So there's a lot of stuff that I'm kind of assuming that you're getting as we go, and that you can call all of that forward as needed to help us make decisions about what this graph will look like. So this is definitely a building kind of course where you're learning and adding to that learning on top of what you already know to proceed. So really everything we learn in math builds on itself, which means you really aren't allowed to forget stuff that you've learned before, because you're going to need it again. And you'll be expected to have mastered that material. Okay, so anyway, back to this. 0 and then its coterminal angle 2 pi. We should be able to complete a cycle in going from 0 to 2 pi because they're coterminal. So let's see if that's true. I think it is, but let's double check it. So taking our values that we learned from before, the quadrantal angles, cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is -1, cosine of 3 pi over 2 was 0, and get back to 2 pi, back to the positive x-axis, and the cosine of 2 pi is 1, just like it was for 0. Okay, cosine of pi over 6 is square root of 3 over 2. Then cosine of pi over 4 is square root of 2 over 2. Cosine of pi over 3 is 1/2. Are you seeing some values that you've seen before quite recently? Well, yeah, we've seen these same values when we were talking about sine of x. And no surprise, cosine, its cofunction, has very similar answers. Just remember the identity we had with the cofunction identities. Cosine of x equals sine, its cofunction, of the complement of x, so pi over 2 minus x. Okay, well, anyway, it's not surprising to me that we're getting back some of the same answers we did when we talked about sine. Okay, so let's make the x-axis marks every pi over 2, and the y-axis marks every 1. I gave myself way too much y-axis, but that's okay. We'll live with it. Okay, so 0, plot 1. Pi over 6, square root of 3 over 2 is that 0.866 number. Pi over 4 is square root of 2 over 2. That was 0.707 or so. Pi over 3 is 1/2. Pi over 2 is 0. And so the curve we get looks very much like the curve we just got, just in a different way. It's the same numbers, just in a different order. So when we get to pi over 2 at 0, pi we get to -1, low value, right? 3 pi over 2 is 0, middle value. 2 pi, we're back to the high value of 1. In fact, the fact that sine and cosine are cofunctions should be an indicator that they have a very similar shaped graph. So cofunctions have very similar graphs to each other. And so this one is a sinusoid graph as well. Okay, so going from right to left, we've got high, middle, low, middle, high. So going left, then middle, then low, then middle, then high. And if you can place those dots correctly, those few dots, and if you know what a sinusoid is supposed to look like, you can draw a pretty decent graph. I'm not real happy with that last part of that one, so, well, that's even worse. I'm going to leave it. If you look at the notes, you'll see better renditions of these that a computer generated. The pictures, they're better than my pictures. All right, so let's answer a few questions about this one. What is the domain of this function? Well, like sine, it's all reals. What is the range? Well, again, we have a low value of -1 that is actually used, and 1, which is also actually used. So that's our range. So it has the same range as sine of x does. What is its period? Well, as we saw earlier, this is a period of 2 pi for the same reasons as above. You could go from this high mark at 0, the next time we're at a high mark is at 2 pi, so that horizontal distance between high values is 2 pi, meaning the period is 2 pi. Okay, this is a continuous function. No discontinuities at all, so it's a nice continuous function. What are the x-intercepts? So again, I want a generic way to list all of them in one expression. So I'm going to have to think about this a little bit harder than the last one. The other one was a little bit easier. So I'm going to list a few of them. The x-intercepts are pi over 2. The next one is at 3 pi over 2. And I'll tell you a few more of them without having actually graphed them. The next one is at 5 pi over 2. Then after that at 7 pi over 2. Are you catching the pattern? Okay, and then let's go to the left sum. -1 pi over 2, or negative pi over 2. -3 pi over 2. What's the one before that one? I hope you said -5 pi over 2. And it keeps on going before that. So do you see that every one of these is odd number times pi all over 2? So this is what we call an odd multiple of pi over 2. Whereas for sine, the x-intercepts were multiples of pi. So let me go up here and write that up here so that that statement is parallel to the one below. This one is multiples of pi. Okay, so we took an integer and multiplied it by pi to get n pi. So this one down here is a little bit harder. How do we write I want an odd number, assuming n is an integer? Well, to start getting an odd number, let me ask you how you could guarantee that the answer is even. What could you do to any integer to create an even number? Well, hopefully you're thinking, well, if I multiplied that integer by 2, that's going to make it even. 1 times 2 is 2, even. 2 times 2 is 4, even. 3 times 2 is 6, even. 4 times 2 is 8, even. 5 times 2 is 10, even. So if we double an integer, we get an even number. So if we have an even number, what could I do to that to get an odd answer? Well, there are two possibilities that are normally used. We're going to use addition by 1. So any even number plus 1 is odd. The other way you could do it is to subtract 1. Any even number minus 1 will give you an odd number. So if you want an even number, it's 2n, where n is an integer. If you want an odd number, it's 2n plus 1, where n is an integer. And so what we want is an odd multiple of pi over 2. Okay, so that makes our x-intercepts an odd number multiple of pi over 2. And that's the set of all x-intercepts. Let's see, what have I... Oh, symmetry. This graph is symmetric with respect to what? I hope you are thinking symmetric with respect to the y-axis. Any graph that is symmetric with respect to the y-axis is called an even function. And every even function can be identified by this test. If you put negative x into the function and simplify, you'll get back the original function f of x. So that means that because we have symmetry with respect to the y-axis, which implies that it's an even function, and that means f of negative x equals f of x, then that implies that cosine is an even function. Okay, and so back up here, with the even odd identities, we are now going to write the identity for cosine in this list. The cosine of negative x will give us back the original cosine of x, meaning it's even, meaning its graph is symmetric with respect to the y-axis. I think this one may be easier for you to understand. If you have symmetry with respect to the y-axis, if you pick any point whatsoever that's on the curve and draw a line perpendicular to the y-axis and measure it, then go the other side of the y-axis the same distance, you will land on a point that's on the curve. So any point whatsoever, pick this one, there's its symmetric point. Pick this one, oh, let me make it a different color. I'm not going to draw all the lines because it makes a messy graph, but like if you picked this point, its symmetric point is over here. Okay, so this is definitely symmetric with respect to the y-axis. You can tell that from the graph, which means it's an even function, which gives us the even odd identity cosine of negative x equals cosine of x. Okay, let me see. Now, one of the things you learned, I hope, in an earlier course in college algebra, I would think, when you were graphing, and if not, you can treat this as if it's brand new, and that's the way I'm going to teach it, is that you can alter a basic function with different transformations. And this is as a big topic called transformational graphing. And the things that you're allowed to do with transformational graphing is you can stretch or shrink a graph vertically or horizontally. You can reflect a graph. You can shift a graph. Oh, reflect, you can do reflection horizontally or vertically. You can shift a graph. That's called a translation. You can translate a graph horizontally or vertically. And those are the things that we include when we talk about transformational graphing. And so in kind of a generic sense, if you have an original function f of x, you can do all kinds of things to that. And I'm going to list all of the possibilities in one big equation, but we're going to slow this down and take them one at a time. But I'm going to give you the big picture first. y equals, we could multiply f of x by some constant a. Inside, we could multiply the variable x by a number. I'm going to call that b. A number could be added or subtracted from x before that multiplication occurs. I'm going to write it as subtraction, and I'll explain that later, why I made it subtraction. And then you could take that final answer you just got and add a number to that. And so those four things allow us to do the transformations I listed earlier: stretch, shrink, reflect, and translate. Those are the things that these letters can do. And all of those can be done horizontally or vertically. And that takes care of every single one of those four letters. Each of those four letters has an effect on the graph, which can be described in one of those ways: stretch, shrink, reflect, translate, horizontally or vertically. All right. So I'm hoping that you remember this. I'm going to do an example that perhaps you already have encountered before. If I started with y equals x squared and asked you to graph y equals 3x squared from the graph of y equals x squared. So I'm going to set this up. It'll take me a second to get my markings on the axes where I want them. So give me a second. You're thinking, oh my gosh, how far is he going to go? I shouldn't have picked the number 3. I should have picked a smaller number, but that's okay. I'll live with it. All right, so I'm going to graph this original graph in green, I guess. So you know what y equals x squared looks like. It has points 0, 0, 1, 1, 2, 4, 3, 5, 6, 7, 8, 9, 3, 9, 4, 16, which goes beyond my axes that I allowed for, and then -1 will give us 1, -2 gives us 4, -3 gives us 9. And of course that one's nice and symmetric with respect to the y-axis. So of course y equals x squared is an even function. Just saying, just so that you get a good idea that everything that we do, oh wow, that last part looks bad. Everything that we talk about can be brought into the discussion again and again and again. So I'll try to bring up topics like that that are being used again and again, like symmetry with respect to the y-axis, which means y equals x squared is an even function. Okay, so enough of that. Now I'm going to graph the transformed graph in red. Now what happens is that we get the y value of our normal x squared graph and multiply that output by 3 before graphing. So 0 times 3 is 0. The output 1 times 3 becomes 3. The output 1 times 3 becomes 3. At 2, the output is 4. 4 times 3 is 12. So at 2, the output is now 12 instead of 4. And same thing at -2. And so that has the effect of stretching the graph vertically. For each x, the y-coordinate is now 3 times as far from the x-axis compared to the original one. So this has stretched, or it stretches the original function vertically by a factor of 3. Okay. So let's now apply that idea, and by the way, that's the A we're talking about in my generic equation up there at the top, to a trig function. So if I start with y equals sine of x, and we now know what that graph looks like, and I ask you to graph y equals 2 sine of x, we now know that that's going to stretch the graph of sine of x vertically by a factor of 2 this time. So let's graph good old sine of x. And the difference between the two sinusoids, and so you can kind of keep track of which one is which, is if you can remember what happens for 0, when x is 0, you can graph the two sinusoids, sine and cosine, very easily. So let me get this set up and I'll show you what I mean. Okay, so you need to commit to memory, I would say. Commit to memory that sine of 0 is 0, so it starts at the middle. Cosine of 0, on the other hand, is 1, so it starts at the high. So after the middle for sine, we're going to go middle, then high, middle, low, middle. And extending that to the left, we've got high at pi over 2, then middle, then low, middle, high, middle. Draw your nice sinusoid through those points. Isn't it sort of gratifying that it only takes a few points and knowledge of the shape of the curve to get a pretty decent graph of a sinusoid? And we didn't take 6 months to figure this out. This was pretty quickly done, so that makes me very happy that we can do that. Okay, so now let's graph y equals 2 sine of x. So every output is going to be doubled. So I'm going to say the output at each x, double it, and plot it. So at negative 2 pi, the output is 0. 0 times 2 is still 0. Then I'm going to move to each mark over to the right. So the next mark to the right, we have a high of 1. 1 times 2 makes the new output 2. 0 times 2 is 0. Negative 1 times 2 is negative 2. 0 times 2 is 0. 1 times 2 is 2. 0 times 2 is 0. Negative 1 times 2 is negative 2. 0 times 2 is 0. It's still a sinusoid. Stretching a graph doesn't change its nature. It just changes the y value. And so every point has been stretched away from the x-axis to twice its original distance from the x-axis. Okay, so that's what A can do when A is positive, and I probably should have said that. 3 and 2 are both positive, so well, I'll leave it at that. Just notice that A is positive, and we'll come back to that in a minute. What else A can do? Amplitude. I want to define that word. Sinusoids have amplitude. The other ones don't have amplitude, but sine and cosine will have amplitude. And my definition of amplitude is the following. It's the vertical distance between a middle value and a high value. Okay. So if you look at the normal sine function here, the one that's in green, the middle value is 0, the high value is 1. How far is it from 0 to 1? 1, right. So its amplitude, which we're going to abbreviate AMP, is equal to 1. Now let's look at the one that's been stretched. The middle value for 2 sine of x is still 0, but its high value is 2. How far is it from 0 to 2? Well, it's 2. So the amplitude of this is 2. So do you see in the equation what's causing us to get an amplitude? Well, so far it looks like it's the number in front of sine of x, the understood 1 times sine of x in the first case, and the visible 2 times sine of x in the second case. So part of what the A gives us for the sinusoids is it gives us an indicator of amplitude. For the other ones, it will still be a stretching factor, a vertical stretching factor, but we won't associate the word amplitude except for with sine and cosine. All right. The textbook's definition of amplitude is different. They say it's the average of the distance between them, and so they have a formula for that, and you can do that if you want. So let's say we're talking about the second one. The high value is 2. It's half the difference. I said average, didn't I? That's not what I meant. Therefore, I don't do it their way, so that's why I got confused for a second. The difference between the max and min. So the max is capital M, is the way you can represent that, minus the minimum value. So minus -2, the lowest value is -2, divided by 2, divided by 2. That's their formula, if you will, for amplitude. And it works. There's nothing wrong with it. 2 minus -2 is 4, and 4 divided by 2, of course, is 2. They got the same amplitude for y equals 2 sine of x that we did. So it's no surprise that they got the same answer. I just like my definition better, probably because that's the way I first learned it. And I think I learned it in a physics class, but nevertheless, that's the way I describe amplitude, and to me it makes sense. But if you want to use their formula, there's nothing wrong with that. I think I've said this before. In mathematics, there are usually several ways to do anything that we are interested in doing, and so as long as you do something mathematically correct that leads you to a correct answer, it doesn't really bother me. So if you want to use my definition of amplitude or theirs, just do it correctly and get the right answer, and I'll be a happy camper. Okay, so now let's talk about what would happen if A were negative, because that's actually kind of a different thing. So let's graph, let's use a color we haven't used yet. Let's graph y equals negative sine of x. Well, it's still multiplying by a constant. It happens to be -1. So when we go to graph this one, I'm going to give it its own grid. We're going to take the regular values of sine of x. So we're going to be looking up there at the green one for our inspiration as to what our outputs for the normal graph would be, and use those to get the outputs for this one. All right, so sine of 0 is 0. 0 times -1 is still 0. At pi over 2, we're expecting an output of 1. 1 times -1 is -1. Sorry, I wrote the pi over 2 in the wrong place. Oops. At pi, for the regular graph, the answer is 0. 0 times -1 is still 0. At 3 pi over 2, third mark over, the output is -1. -1 times -1 is +1. And 0 times -1 is 0. Then going this other way, it looks like we have a pattern now of middle, low, middle, high, middle, low, middle, high. So going this other way, low, middle, high, middle, low, middle. and graph that. It's still a sinusoid. So how is the green one up above related to this one? I don't know if you caught one of the words I used earlier, but this is a reflection of the graph of x of y equals sine of x over the x-axis. And so I'm going to refer to this sometimes as a vertical reflection because the y values are changing. 1 becomes -1, -1 becomes 1. So we're reflecting vertically because the y values are the things that are changing. There's also something called a horizontal reflection, which I don't think we're going to really need in this course. It does exist, and it occurs, I'll just say it because I've brought it up now, if you multiply the x inside of the function by -1, it reflects it horizontally. But like I said, I don't think we're going to see that in this course, so it's not something I'm worried about at this stage. Anyway, multiplying by negative makes you have a reflection vertically. And for right now, you can think it reflects it over the x-axis. But it's not always going to be over the x-axis, as we'll see later. Sorry, don't mean to burst your bubble, but that's why I want to say vertical reflection on purpose, because it may not be the x-axis that we're reflecting over all the time. So what would happen if I graphed y equals -2 sine of x? Well, again, I'm going to take the regular outputs, the green outputs up there. This time I'll multiply by -2. So at 0, the output is 0. 0 times -2 is 0. The pi over 2 output is 1. 1 times -2 is -2. 0 times -2 is 0. -1 times -2 is +2. And 0. And you can see the sinusoidal nature. So this over here will be high, middle, low, middle. And so this has done two things. It's reflected the original green graph up there over the x-axis. It's reflected it vertically, but it's also stretched it vertically. So with this one number, -2, the negative has one effect, makes it reflect. The 2 has a different effect. That makes it stretch. So the -2 does two things. So this one, we would say reflection, well, vertical reflection. I'll put it that way. Vertical reflection and stretch vertically by a factor of 2. Okay, so the reason I started all of this talking about -a was on purpose. I wanted to talk about amplitude when a is negative. So if I measured the amplitude for the y equals negative sine of x, using my definition, the middle value is 0, the high value is 1. How far is it from 0 to 1? It's 1. So the amplitude for this one is 1. Is 1 the coefficient of this function? Well, we're going to have to figure that out. So let's see if we can go another step. Let's look at the other one. For y equals -2 sine of x, the middle value is 0, the high value is 2. What's the amplitude? Well, it's 2. Again, the amplitude is related to a, but it's not necessarily a itself. So here comes the definition of if you have y equals a sine of x, the amplitude will always be the absolute value of a. Because amplitude is a distance, it has to be a positive number. If your coefficient of sine of x is -2, you have to take its absolute value to get the distance it's going to from middle to high value. Okay? So that's how we're going to find amplitude. And by the way, that's going to be true for y equals a cosine of x as well. The same thing happens. So I'm just going to state that as a truth before you get too worried about it. Okay, so that deals with a. What happens if we do an a multiplication? It can reflect if a is negative vertically, and the absolute value of a will give us the amplitude. All right? So let's go on to the next topic now. Okay, so now let's start talking about the next topic, which is y equals sine of bx. That is, if x is multiplied by something. So to start that topic, I'd like for us to, again, have y equals sine of x as a basis for all sinusoids, and compare that to what would happen if I had sine of 2x. Okay, so you may remember that multiplying by x also has a stretching and shrinking effect. And this is where if that had been -2x, that would have caused it to reflect horizontally, that is over the y-axis, which we're not going to do in this class, I don't believe at all, but I'll just give it a nod as it could be done. So let me set up the axes for the vanilla plane normal function. And this one's going to be a little bit painful the first time through, and then I'll teach you a way to make it easier. So please just bear with me on the first round, and then it does get easier. Okay. So sine, let's do regular sine in this color, I guess. So sine of 0 is 0, so middle, high, middle, low, middle, going the other way, low, middle, high, middle. And to do this second one, I'm going to make a table of values. Actually, let me back up and make it a little bit more information. So we're going to find out what, given an x, we're going to calculate 2x, and then what's the sine of 2x is what we're going to do. Okay, so let's start with 0, and let's do pi over 6 and pi over 4 and pi over 3 and pi over 2 as a starting point. And we'll see if that's enough information to figure out what's going on. My hope is that it will be plenty of information. So 2 times 0 is 0. 2 times pi over 6 is pi over 3. 2 times pi over 4 is pi over 2. 2 times pi over 3 is 2 pi over 3. And 2 times pi over 2 is pi. So ignore the first column for a second. We're looking at the middle column, and we're going to take the sine of those numbers. So sine of 0 is 0. Sine of pi over 3 is square root of 3 over 2. Sine of pi over 2 is 1. Sine of 2 pi over 3 is square root of 3 over 2. And sine of pi is 0. Okay, with me so far? Alrighty, so now to graph this, we're going to graph this one in red. Really hold on tight here. Ignore the middle column now. We're going to take, for a given x, like 0, what's the output? 0, okay? For a given input, pi over 6, what's the output? Square root of 3 over 2. For a given input, pi over 4, what's the output? 1. For a given input, pi over 3, what's the output? Square root of 3 over 2. For a given input like pi over 2, what's the output? 0. It's still sinusoidal. But instead of it taking from 0 to pi to go from 0 up to 1 and down back to 0, it's now happening within a space of pi over 2. So it is a stretching or shrinking thing that's going on here, but this is not stretching. When it was 2 sine of x, it stretched it vertically. It was twice as far from the x-axis. And so you would think that sine of 2x would have the same effect. You would think it would stretch it horizontally out, and it doesn't. It actually shrinks it. So one of the things I want to talk about here as a theme is that anything done to x inside the parentheses has a horizontal effect, so it'll change things to do with x. So it has a horizontal effect opposite of the expected effect. So when you multiply by 2, you think you're going to make it bigger, so it'll stretch out. It actually shrinks it, and it's half the distance from the y-axis compared to the original. So like this high point on the green one at pi over 2, it's now half the distance from that point to the y-axis. And so it's shrunken it, it's compressed it horizontally by a factor of 2. So let me write that down. This is the effect we're seeing, is it doesn't stretch, it compresses horizontally by a factor of, and for this we'll use the reciprocal, by a factor of 1/2. Okay, so everything is half the distance from the y-axis as it would have been originally. So once you get that idea, instead of every mark having a major event like high, middle, or low, it's going to be every half mark. So at 0 it's middle, half of the way to pi over 2 it's at the high, at the second halfway, so at the mark, sounds weird, but anyway, every half mark something happens, so middle, high, middle, halfway between will be the low, then at the mark it'll be back to 0, halfway high, mark 0, halfway low, mark 0, and draw the sinusoid. Okay, and the same thing will happen on the other side. Halfway low, middle, halfway high, middle, halfway low, middle, halfway high, middle, like that. And so I'm going to point out a couple of points where they started and where they ended. This point got compressed into there. This point got compressed into there. That point got compressed into there. Okay, does that make sense? So it's all been compressed horizontally by a factor of 1/2. So, big question is what's changed in what we've talked about already? Well, remember the period is the horizontal measure before it starts repeating itself. So now it's completing a cycle by the second mark, and the second mark is 2 pi over 2. So from here to there is pi. That's the period. The red one is completing a cycle, middle, high, middle, low, middle, within pi. So the period is what has changed. The amplitude has not changed. The amplitude is still 1 because we don't have a number in front of sign to change the amplitude from the normal 1. So the period has become pi, and if we were asked about the amplitude, we could certainly say it's the absolute value of the invisible number 1 in front of sine of x. So the amplitude's 1. But how are we going to calculate the period? Because I don't want you to have to graph it first. I'd like for you to know what's going to happen before you graph it so that you can kind of get a handle on it. Well, as it turns out, whenever you have the period of sine or cosine, the basic normal period is 2 pi, right? Well, instead of multiplying by 2, we're actually dividing each x by 2, so it's closer to the y-axis. And so it makes the period half as much. So in a general sense, the period will always be for sine and cosine the normal period, which is 2 pi, divided by the absolute value of b. Now, in the book, I think they say just divide by b because we really don't encounter, as I said earlier, that negative x in this book. I don't think we do it at all. But in a more general sense, I'd like for you to know more than just that. So it's technically divide by the absolute value of b, but I'll tell you that it's going to be just b in this book because b is never a negative number in this book. But I want you to know more than that. So that's the formula for the period. Okay? It's a little bit more complicated than amplitude because remember amplitude, and this is a review, the amplitude is the absolute value of a. Really simple formula. The period is more complicated. It's the normal period 2 pi divided by the absolute value of b. Okay? So that gets us started with those two ideas. And by the way, we've been using sine as a basic function. I could have done all of this with cosine and the results would have been the same. So don't think that I'm sliding cosine by not having done any of those yet. With the example, I've used sine every time. But in our examples, I'm going to do some cosine things as well. So let's graph y equals cosine of 2/3 x. Okay. So this is how I would suggest you go about doing this. Find the amplitude, which is the absolute value of a, and there's an understood 1 in front of cosine, so the amplitude is the absolute value of 1, which is 1. Even though it's kind of like, well, that's what it always is for the normal function. Yeah, you're right. I'd like for you to go ahead and give it a nod so that you think about it, so that when it's not 1, you know that it has to change. You've got to do something about it. Okay? The period is the normal period for cosine, which is 2 pi, divided by the absolute value of 2/3. Of course, the absolute value of 2/3 is 2/3. To divide fractions, you multiply the numerator by the reciprocal of the denominator, which I took the absolute value away because it is 2/3, and that becomes 3 pi. Now, there's something I haven't talked about yet, which is probably something that you should hear me say. If we look at the normal, let me go up to a picture where it's not got so much busyness on it. If we look at a normal sine curve, way back here at the beginning, or cosine curve, either one, the major points that we're graphing, after we did all of the little bitty points on this first graph, the ones we're graphing are the ones that are middles and highs, middles, lows, and middles. Those are the ones we're doing. And so if we go from 0 to 2 pi, including the ends, we have 5 points to deal with. So if we put in 0 is a point, and then the pi over 2, pi, 3 pi over 2, and 2 pi are our 5 points. Well, that divides that 0 to 2 pi region into 4 equal parts. 1 goes from 0 to pi over 2, 2 goes from pi over 2 to pi, 3 goes from pi to 3 pi over 2, and 4 goes from 3 pi over 2 to 2 pi. And in fact, we call those 4 regions the 4 quadrants. Okay, so this is not a coincidence. This is a real thing. The period is split into 4 equal pieces horizontally. So to find out where these major marks are between, if I took the distance from 0 to 2 pi, which is 2 pi, the normal period, and divided it into 4 equal parts, and calculate that, that's going to be pi over 2, and that is the length horizontally of every mark on the x-axis, is pi over 2. So that's what we're going to do. So we've explained it up there. Let me go down here and explain it with this example. Whatever the period is, take the period and divide it into 4 equal parts. So the period is 3 pi, we just calculated, divided by 4. And reduce that if you can. That doesn't reduce, so I'm happy with it as is. And what we're going to do now is what I alluded to earlier, is sometimes we intentionally distort the graph. So if there's a period change, a lot of times we're going to distort the graph to make it easier to do the graphing. So instead of making this first mark be a length of pi over 2, I'm going to make it 3 pi over 4. And so we're going to make a mark, and every one of these marks is another pi over 4, 3 pi over 4. So this is 6 pi over 4, 9 pi over 4, 12 pi over 4, and I know a lot of those reduce. Negative 3 pi over 4, negative 6 pi over 4, negative 9 pi over 4, negative 12 pi over 4. And you can reduce those if you need to know those x-coordinate values. I'm going to go ahead and leave the marks on the y-axis, and this is the distortion. I'm going to make them about that big. And 3 pi over 4, 3 times about 3 is 9/4, so that's about 2.25 or 3. And that isn't to scale. That's fine. We're intentionally distorting. It's okay to do so. So what I would do is, to plot this graph, I would think, well, cosine of 0. I would substitute 0 into my function. 2/3 times 0 is 0. The cosine of 2/3 is the high value of 1. Then the next thing that's going to happen is when I slide over a fourth of the period, so one of these marks, it's going to be at the middle. Next mark over, it'll be at the low. Then the middle, then the high. That's so easy, right? As long as you put the 3 pi over 4 as an indication of what each one of those marks means, you've now created a perfect graph. For the right side, let's go this left side, so middle, low, middle, high, and there's your graph. Oops. It looks just like what cosine of x would look like, but the only big difference here is that the mark on the x-axis, instead of being pi over 2, it's now 3 pi over 4. And again, we got that from dividing the period that we calculated by 4. Okay, take the period that you calculate using 2 pi over absolute value of b, then take that answer and divide it by 4, and that will be the horizontal distance between these major points, the highs, the middles, and lows, and middles, and highs. The horizontal distance between them is 3 pi over 4, and that's how you can get that done. That's what I would do if I were you. It's the easiest thing. So you can see I've got some instructions written out how to do this, how to think your way through it. So that's kind of what I'm doing each time I do one of these. So you might want to read through those and follow through that as I do the next example to make sure that I've done everything correctly. I'm going to need to move to the next recording because I've run out of room on this one. So I will be talking to you again in the next part.